Hello. In this video, I wanted to continue where I left off with the finite square well potential. If you recall in our sort of live lecture, we went through some of the introduction of the finite square well potential and kind of set up the thing and did a whole bunch of algebra to kind of wind up at this point that you see at the whiteboard. And at that point, I said, that's enough for doing live. I don't want to sit here and do algebra all day, but I wanted to, in a video, kind of go through some of the details of how you get from here actually to a solution for this finite square well potential. So if you remember, what we did is we had a potential that looks like the picture on the upper left, and we divided it up into three regions, and then we solved for the most general possibilities of the wave function in each of the three regions, and we matched up the boundary conditions, which gave us the first two equations, and also we matched up the function at the boundaries, which gave us the first two equations, and then also matching the derivative of the wave function at the boundaries gave us the second two equations. And at that point, we kind of stopped. So I wanted to pick up with that here, because actually, we still have to rely on the computer a little bit, but we can get to a much nicer place, actually, by taking advantage of the symmetry of the problem. So like I mentioned when we were live, is that we could pick our 0 for x to be anywhere. In this case, I wrote these down by basically picking 0 to be in the middle. That meant, unfortunately, that the sides of our potential were at negative L over 2 and L over 2 if we said that it's L wide. And so it makes this look a little bit messier, because if we could have picked 0 to be at, for example, the left edge, that would have made some of these equations look a little nicer. However, picking 0 to be in the middle lets us exploit a little bit about the symmetry of the problem. Because what we can do is we can look at this and we can say, okay, if 0 is right in the middle here, then everything physical, all the physics that comes out of our solution should be symmetric around 0, because the potential is symmetric around 0. So everything that we get out of this, should be symmetric. And that means the wave function should be symmetric. Or there's one other possibility, because the wave function itself isn't what we observe. What we observe is probability. So remember, probability is in this case basically just the wave function squared. It's the wave function times its complex conjugate, but here all the imaginary stuff has been moved into the time-dependent part. So here we're just dealing with a purely real wave function, and so probability is the wave function squared. So our wave function can be either symmetric or it can be anti-symmetric. It can do the opposite thing on the left side as it does on the right side, because when we square it, it just gets flipped positive again, and the probability itself will still be symmetric. So we can use that to simplify these equations a lot, because what we could do is we could say, okay, when we solve for this, our wave function is either going to be symmetric or anti-symmetric, and let's just go through those two cases. So for example, if the wave function is symmetric, then we can immediately look at this and say, okay, on the left-hand side, we have A as our amplitude as an exponential going up, and on the right-hand side, we have F as the amplitude of an exponential going down. If it's symmetric, that means, I'll write that down here, symmetric. In a symmetric case, that means capital A is just equal to capital F. That's what it means to be symmetric. It also means in the middle region, region 2, we can't get both sines and cosines. The only function that's symmetric there is the cosine. So C is 0. So that makes things a lot simpler for us. And then for the symmetry, the anti-symmetric case, we have something similar. There, that just means A is going to be equal to minus F. And there, the anti-symmetric or odd function there is the sine and not the cosine. So that means there's no cosines, that means D is 0. So if we put in those simplifications, that will clear this up a whole lot. And so, for example, these equations, I can cut them out. Instead of 4 equations, I basically cut them down to 2, because originally I had A, C, D, and F. basically, and I have 4 equations involving them. Now I have, in each case, in the symmetric case, I've gotten rid of F here by just saying it's equal to A, and I've gotten rid of C because we just 0. So I'll wind up with just 2 equations in each case, and it's a lot easier to manage. So let me go through, I'll mainly just do the symmetric case because the antisymmetric case looks very similar, but just write that out. So let me remember these equations or go rewind the video, but I'm just going to go through the symmetric case. I'm going to rewrite these for the symmetric case. So for the symmetric case, we have A equals F and C equals 0. And so our equations turn into, we just have A, and then we had times e to the minus k prime L over 2. And then we had, that's equal to, we had a sine term, which we're not going to keep that because that's not symmetric. And then we had a cosine term, cosine k L over 2. That was one of our equations. And then the equation involving the derivatives was basically this: a k prime, same exponential, equals d times k, and then the sine kl over 2. This was a sine function because this was an equation that came from the derivative of the wave function. So those are our 2 equations. We can put these together actually rather easily. I'm basically going to divide the second row by the first row and get k prime equals k, and then sine divided by cosine is really just tangent. So that is actually very useful because this is what is going to help us figure out what the allowed energies are. Because remember, k and k prime themselves really just depend on the energy. For reference, let's write that down. But if your k prime was square root 2m v naught minus e over h bar, then k was just square root 2m e over h bar. That's a v naught minus e up there in case that's hard to read. So if we put this together, we get basically an equation that involves E and the energy and a bunch of constants that we would typically be given in a problem, like the mass of the particle that we're describing, or the potential energy, the depth of potential energy well, and then h bar is just a universal constant. And we also have over here the width of the potential well. So those are all things we could know. And then, so what we're going to find is we're going to find an equation basically for E. And so let me do a little bit of writing this out. I'm going to move the k here to the other side and write this as k prime over k equals tangent. But when I'm going to then substitute this in for k prime over k. So when I do k prime over k, all the stuff that's same here cancels. And I wind up with square root v naught minus e over e, square root e, equals, that's the k prime over k term. And then the tangent, I'm just going to write in what k is here. And I'm actually going to, I'm going to write basically root 2me over h bar and then an L over 2, but I want to move everything inside the square root here. So I'm going to write this as 2me, and then I'm going to have an L squared, because I'm moving it inside the square root, over 2, move it inside the square root, becomes a 4, and then an h bar squared. So I've got 2 over 4, so I can just simplify that into 1/2. So I have tangent of square root, this big mess, MEL squared over 2h bar squared. The reason I did that is I wanted to emphasize the units here and the number of independent things we actually have. So V naught isn't in energy units. It's just something that has the same units of E. So if we're measuring things in electron volts, as we typically do, then V naught is in electron volts. So that's one of our relevant energies in the problem. You notice everything here, we have a bunch of stuff, but all that ever, it only appears over here, and it just appears in this combination. And the tangent of something, when you take a tangent of something, it has to be dimensionless. It has to be an angle. Angles are really ratios. They don't have units. So what that means is I've got an energy here, and then it means the rest of the stuff combined has to be basically inverse energy. Or another way of saying that is that 2h bar squared over ml squared also has energy units. These three things all have energy units. E, of course, is an energy. V naught is an energy, but also 2h bar squared over ml squared is an energy. And the key point there is just that, yes, we have these sort of unknown constants in our problem, mass and length of the width of the potential. But we can turn that, what really matters is their combo, and we can turn that into an energy unit. And the reason I'm writing it this way is, now that I've got it at this point, I basically want to solve for E. But this is a nasty equation to solve for E. It's what you call a transcendental equation. It's not easy to really go further, as I mentioned in class. So we really can't do much more with this on the whiteboard. But what we can do is we can, one of the nice things we can actually do is we can plot it. We've got two functions of energy on each side of the equal sign here. And we can just treat that as two curves and see where those curves intersect. And where they do is where our solutions are. So that's one nice way of thinking about this, this problem. And so that's what I'm going to flip over to. I'm going to flip over to Wolfram alpha, and I'm just going to basically plot these. But to make things simpler, since my relevant constants here are basically, so E is going to be my variable. I'll just call that X when I make the plot, just to make it easier to type. My other relevant combos that are energy, in terms of energy, are V naught and 2h bar squared over ml squared. So of course the easiest thing for me to do when I make this plot is I can just set those equal to 1. And then plot the result. So that's what I'm going to do, or that's what I already have done over here. If I come over here and I look at Wolfram alpha, which you should see in the screen now, make it a little larger, is I've told Wolfram alpha to solve square root of 1 minus x over x, that's basically this left-hand side, equal to tangent square root of x. And everything else I just set equal to 1, so it's not even there. So I just told Wolfram alpha to solve that for x, and it even made it gave me a number, but it also made this nice little plot for me. It really illustrates. This blue curve is the square root 1 minus x over x curve, and then this purple one is the tangent. And so what does this mean? What this means is that you notice there's only one place where these lines intersect. So what it means is that for the symmetric case, at least, I haven't checked the anti-symmetric case. I get a slightly different set of equations for that. But for the symmetric solutions, there's only one. There's only one energy allowed. And that energy is basically 0.546 of times the V naught, because remember I set V naught equal to 1. So E, if E is 0.546 here, that just means basically compared to V naught is the relevant thing. Now, this means that there's only this one solution in the case where 2h bar squared over ml squared is also equal to V naught. So what we can think of that is, how does the depth of the well, which is V naught, compared to the width of the well, which is related to L. And so in this case, we have only one solution where that fits inside the well. If we go any higher in energy, we wind up outside. We wind up with E above V naught, and we don't have any more solutions that are actually contained within the well. However, if I want to find a different case where maybe the well is deep compared to the width of it, then I can just basically come up here and change, instead of 1, let me change, instead of considering V naught to be 1 in these units, let me take V naught to be, I don't know, 100. And so really all I'm doing here is I'm changing the scale of V naught relative to 2h bar squared over ml squared. Because I'm basically going to keep this term as defined as 1, but I'm saying V naught is 100 now. So I'm just doing a different case here. So if I do that and ask Mathematica or Wolfram Alpha to plot it, it thinks for a little bit. And in a second, though, it should plot it. Here we go. And now it looks different, actually. It gives me a couple results. Actually, one of them's hiding up here. It doesn't even show it quite on the plot, but there's a solution. So now if V naught is 100 in whatever units, then there's a solution for E equals 2. You can't even quite see it on the curves, but there's a solution up here where those lines cross. It's actually off the scale. But there's another solution where E equals 18.2. There's another solution that doesn't list it here, but you can see these lines crossing. There's another solution right around E of about 50 or a little more. And then there's another solution, a fourth one, right around 90, E of around 90. And then you get up to 100 and there's no more chances. And so what that means is that in this case, if I just look at the symmetric solutions, I actually get 4 of them, 4 allowed energies. And given what we know about the wave function, there's probably, they should alternate, just like the standing waves. Let me flip back to the whiteboard. You remember just, standing waves in a string. I draw that in the corner. Remember that basically these looked like, there's a symmetric one, there's an anti-symmetric one, there's a symmetric one, there's an anti-symmetric one. They basically just alternated. And we don't really expect, that was sort of the case for the infinite square well, but if we just sort of say it's deep and not actually infinite, we don't expect it to really change very much. We expect this alternation of symmetric and anti-symmetric. So what this means here is for the case where V naught is equal to 100 times 2h bar squared over ml squared, is that we get 4 of the symmetric wave functions, and then in between, there's in between each of those solutions, there's going to be an anti-symmetric wave function solution. So there's at least 7 solutions here. The simplest solution is always going to be symmetric, because that's sort of the slowest curving possible wave is going to be symmetric. So that this one where the E is 2.0 whatever compared to the energy units, that's going to be the lowest energy state. And then we should have an anti-symmetric one somewhere between 2 and 18, and then a symmetric one at 18, and then somewhere between 18 and 50, you've got another anti-symmetric one, and then you've got, and so on. So we can actually learn the energies here. And then once we have the energies, you might be wondering what happened to these coefficients that we were solving for. What happened to A and D and stuff? But once we have the energies solved, once we have the energies numerically, if we're given V naught and the mass and other stuff, once we have the energies, we can plug in, solve numerically, and just get numbers for K and K prime. We can then plug it into these equations and basically just solve for example, we can solve for the ratio of A over D. So we can combine, we could rearrange this equation to basically just solve for what A over D is. That gives us the ratio of A over D, and then we can get the combination of A over D by just requiring that the integral of the total wave function overall be equal to 1. Because remember, we also want that. We want probability of finding the particle anywhere to be 1. So in the end, we can now get all the numbers that we need out of this thing. In practice, these coefficients are, in this particular problem, are not even the most interesting things that we can get out of this. A lot of the times what we care about are the energies. So once we get that, we kind of treat it as done. But we could keep going and get A and D out.